wanted to briefly go through some of the things which we have discussed in the last class. This is a 3 credit course. This is an elective from EC department. Um, so this contains roughly these are the things we are going to cover in this course. We'll cover a bit of let me just highlight. Yeah, so this nanoelectronics course will cover mainly some of the advanced devices. Okay, for example, high electron mobility transistor, heterojunction, bipolar heterojunction bipolar transistor. Will cover FinFET, if time permits, bit of quantum cascaded laser. So these are some of the advanced devices we will cover. We'll extensively talk about short channel effect in this course to start with. Now some semiconductor devices, as they are very tiny, we need instead of classical mechanics or along with classical mechanics, we need quantum mechanics. So we'll discuss bit of quantum mechanics in this course. Those are very basic. I hope you know them already, but for the sake of completeness and for the sake of that all of you are in the same platform, we need to discuss bit of quantum mechanics. We will discuss bit of characterization, because nanostructure we can't see it through our naked eye. So we will discuss bit of characterization tools, different kinds of characterization tools. We'll discuss bit of lithography, or how we can fabricate such nanostructures. So lithography can play a very important role. Particularly we will discuss double pattern lithography. So these are different components. Okay, if we see from the top, these are different components which we are going to discuss in this particular course. So there are other courses in the institute which specifically focus on one of these aspects, because for example there are courses where the entire semester they spend on nanomaterial characterization, or there are courses the entire semester they spend on quantum mechanics, and so on and so forth. Okay, so there are other courses, probably other courses like advanced semiconductor devices courses. They only focus on these advanced semiconductor devices. So but here we want to understand and gain knowledge from these different aspects of nano electronics, so that we get an overall idea about nanoelectronics, in which direction we are progressing, how they work, what is the working principle, how we can fabricate them, and so on and so forth. Okay, I hope this course will help you to understand all these. Now so these are different books. Again, I don't want to spend more time on it, but I have uploaded the syllabus in MS Team under file section. So please see it, giving more time. So there are, as you understand, there is no say single book, because I am covering various things. But as and when time comes, I will tell you about the which book I am following. But you can follow other books as long as it is covering the part which I'm talking in the class. Okay, we will also see a lot of internet stuff. We will see papers, journal papers, and conference papers to get more idea, or to get recent research aspects of different things. Okay, related to nano. I also mentioned about the grading in this particular course we are going to follow. This is the thing which we usually do it when the course classes are offline. Here in online, I'm not entirely sure, but probably we'll have 2 to 3 exams. Those exams you need to like write in your answer paper, take a photocopy, or I mean take a screenshot or take a snap of it, and then upload it in the MS Team. There will be other, so those are like a little bit descriptive and little bit mathematical problem based exams. There will be exams, quiz based exams in Moodle. Marks will be given for attendance, marks will be given for quizzes. Quiz and attendance together maybe 20 marks, and rest of the 80 marks will be um, divided among different exams. Okay, let's see how it goes. I will definitely inform you at least 1 week before the exam, so that you get some time, but I will encourage you to go through stuff as and when I am discussing them, so that you are not behind. Okay, uh, so now let's start. uh, let's start where we ended in the last class. uh, so this is the first thing we would like to discuss, which is basically to give you some idea in the direction where this nanoelectronics is progressing. Okay, uh, now to discuss where this nanoelectronics is progressing, one needs to understand, one needs to go through IC roadmap. By IC roadmap I mean integrated circuit roadmap. Okay, I hope you all have heard about integrated circuit. If you open up electronic gadgets, any electronic gadgets, you will see that there are lot of chips inside. Okay, small thing with legs, those are integrated circuit chip, or usually silicon chip. There are other chip also made with other means. There are chips made of other materials, for example gallium arsenide, I mean using 3,5 semiconductor and so on. But predominantly chips will be made of silicon. And how this IC integrated circuit, which contains maybe several thousands of transistors, maybe several millions sometimes, depending on your applications. So we will see how this IC roadmap is progressing, because this is this is highly related or highly associated with nanoelectronics. We will see that how other components, for example MEMS, sensors, can be integrated with this conventional integrated circuit. Okay, probably I mentioned you in the last class also. There are two parallel aspects of research and development, both in the university and also in the industry, but mainly in the university. That is, like in one case, this is the conventional microelectronics or nanoelectronics approach, where you are making conventional active devices like MOSFET, resistor, capacitor, MOSFET, and then resistor, capacitors, etc., using the conventional microelectronics process or conventional CMOS, complementary metal oxide semiconductor CMOS from the process platform. So that is one aspect, and in another aspect, people have been looking for other materials, other structures. For example, MEMS, micro electromechanical system, is a different kinds of structure compared to conventional IC or conventional CMOS process. Okay, so and there are sensors and other things like other nanostructures, nanomaterials, for example non-silicon materials, graphene, MOS2, tungsten disulfide, WS2, molybdenum disulfide, and so on and so forth. They have like carbon nanotube. They are non-silicon material, and steel doesn't have, steel they do not have their space in directly in industry. Okay, to be honest, I mean directly in industry means directly in CMOS industry. Okay, these materials people use in-house, I mean in our lab, university lab, research institute labs, to make devices. Okay, and because some of them has much superior property than silicon, but industry still doesn't see potential. They spend money to fund this kind of research, but still they are not accommodated. They haven't accommodated, or these materials haven't accommodated yet in their process flow. Okay. Yeah. So these are the two aspects in which industry is progressing as far as the nanoelectronics is concerned. In one case, the progress is since maybe, if I may tell you, around 1960 or 1970, from starting from Moore, Gordon Moore. And in another case, this non-silicon or non-CMOS technological progress maybe last 30 years or more. In particularly in universities, because these are areas which are like futuristic areas or futuristic materials, which industry doesn't industries do not want to involve actively. They fund it, as I said. So as the time progress, we will get more picture how the things are progressing when we will discuss IC roadmap. But let me just move on and discuss things, so that we will have this we will get some picture how the industry is progressing, okay, in the nanoelectronics domain. So this is again, this particular site probably I have discussed in the last class. This is a cross-sectional view of CMOS wafer. Okay, CMOS, as I mentioned, complementary metal oxide semiconductor. This is a in which you can develop NMOS, PMOS. Okay, so different kinds of MOSFETs. You can develop resistors, capacitors, inductors, and so on and so forth. Okay. So CMOS, if it is a silicon wafer, it contains like so this bottom grayish piece is basically silicon, where you make your active device in fast few nanometer, maybe fast tens of micrometer, within fast few micrometer maybe. Okay, your active device. Then there are different metal layers. For example, in this particular example, there are metal 1, metal 2, metal 3, metal 4, and so on. If you see present days processes, maybe there will be 7-8 metal layers. Okay, depending on your requirement, and all these metal layers are separated by oxide. Okay, so that they can be isolated. Otherwise they will be shorted if we directly deposit one metal layer on top of another. So they are isolated by oxide layer. These are oxide is particular, maybe mostly silicon dioxide. And at the top there will be oxide and nitride layers. So these oxide and nitride layer at the top is passivation layer, which will basically prevent any outside access of your active device, or so that the devices remains protected. Okay, apart from silicon and metal layers and oxide layers and silicon nitride layers, there will be polysilicon layers also, maybe one polysilicon layer or multiple polysilicon layer. Polysilicon layer is used as gate material. Okay, on top of gate oxide, you need polysilicon to make the gate, to take gate contact. Okay, there might be other there might be other usage. Maybe polysilicon can be used to develop capacitance, or polysilicon may be used to develop resistance, and so on. So my voice is okay now? Is it okay now? And
Yes, sir, it is fine.
whatever I am discussing, is it clear, or I should go much slower? Okay, so these are different. So when we make our integrated circuit, usually what we do, this is again I mentioned in the last class, we design the circuit using Cadence or using Synopsys. These are softwares. We design our circuit, maybe very application specific circuit we want to make, some maybe sensor interfacing circuit, or maybe a simple op amp we have designed, okay, which will be used, or maybe a to D converter we have designed. So what we usually do, we use Cadence or Synopsys kind of software, okay, or Mentor graphics. We design the circuit, we simulate the circuit, so that we can see how the circuit will perform when we apply some signal, and we measure different aspects of it, okay. Then we draw the layout of the circuit, okay. Layout means how the MOSFET will be, because when we are doing the simulation, we just use the symbol of the MOSFET, okay, symbol of the resistor, symbol of the capacitor. But for fabrication, we need to lay out all the layers, of the MOSFET, all the layers of the resistors, capacitors, and so on. Then we send it we can't fabricate such circuit in-house, because it is very difficult and doesn't make any sense to make circuits in-house. None of the, I mean, nowhere in the world people make circuits, even very simple circuits in-house. I mean, I'm talking about using microelectronics platform. I'm not talking about PCB level circuits, okay. So using microelectronics platform, nowhere in the world, in university and research institute, people make complicated circuits. People make means people fabricate complicated circuits. It's not possible. It doesn't make any sense. So most of the semiconductor companies, we usually call it fabless companies, that is, they don't have fabrication facilities. They design the circuit, whether it is university or whether it is industry, and they send it for fabrication to the CMOS industries which have the fab labs. For example, TSMC, XFab, Global Foundry, AMS, all these UMC, all these are the fabrication or fab labs. They take those design and fabricate for you and send you back, okay. So the wafer they use basically look like this. The cross-sectional view look like this. I did mention in the last class that we need several metal layers so that we can reduce the footprint of the chip, okay. If I have a single metal layer and I want to have like I want to, let me just redraw that particular thing which I was trying to which I was trying to draw in the last class. Just if some of you were not there. So what I wanted to want to show you that we need several metal layers to reduce the footprint, that is the size of your chip, okay. And if this is my top view of my chip, okay, silicon chip, which contains several thousands of your device depending on your applications and requirement, okay. And these MOSFETs, resistors, capacitors, etc. So these are this is say my top view. I'm just representing through blocks. And if I need several connections, and if I have only one metal layer, so these are metal connections, okay. So if I need to if I have only one metal layer, you see I need a lot of space to connect all these wires, okay, all these terminals, if we want to connect them through metal lines, which is usually the case. And if I have only one metal layers, say metal 1, I need lot of space. Whereas if I have multiple metal layers, okay, and I have say huge number of devices, which will be usually the case. And if I have metal 1, then I have maybe metal 2 and metal, so say I have my, this is my metal 2, Okay, so I have metal 2, then I have maybe metal 3, okay, and so on and so forth. So I can, so I have my, say this is my metal 3, and I can connect, uh, I can connect, I can go on top of one another because they are separated by oxide. Okay, so within a very small footprint I will be laying out, I will be able to connect them, which is very difficult if I only have one metal line. Okay, so that is why, I mean, we are basically using third dimension, okay, to reduce the footprint. So that is why we need several metal layers. We isolate those metal layers with oxide layers, and if we need, we can remove oxide from a specific place, like here you see these black lines. Okay, in this particular place maybe metal 3 needs to be connected to metal 2, or metal 2 needs to be connected to metal 1, and there oxide will be removed, so there will be a hole will be created, and a metal will be deposited, so that metal 2 is connected to metal 1, metal 3 is connected to metal 2. This is often known as via. Okay, so these vias are useful, to have, so these are known as vias or via. Okay, or if it is a single one, it's called via or vias. Okay, so these are very useful, to connect them if you need. Okay, and if you don't need, they you put oxide between those two layers, and have like, you can separate them. Anyway, so this is a cross section of CMOS wafer, and let's go back to history a bit. Okay, to me there are three milestones as far as the electronics is concerned. One is, all this we know. One is vacuum tube. Okay, uh, uh, discovered by Thomas Alva Edison around 1883. From there, we managed to make diode, triode, pentode, and so on and so forth. And these has huge implications in World War I and World War II as far as this communication is concerned. Okay, communication gadgets is concerned. Gadgets are concerned. Then people managed to develop transistors, particularly in Bell Labs. Bardeen, Bretin, and William Shockley. Around 1947, they make first BJT, that is bipolar junction transistor. Okay, then there is another very important discovery, or invention, which is integrated circuits. Okay, this was done by Jack Kilby around 1958, from Texas Instruments, using germanium to make the IC. And then around same time, Robert Noyce of Fairchild Semiconductor made IC using silicon. Okay, so this is very important discovery, and this is one of their the thing they have made, fast integrated circuit, picture of the fast integrated circuit. So because for this, Jack later on, I think beginning of 2000, he got a Nobel Prize. So these are very important discoveries which set up electronic industry, or electronic device and electronic gadgets scenario at that time. Okay, particularly 1950 onwards, and so on. So this is also, again, I would like to mention, because this has huge implication in IC roadmap. This is known as Moore's law. It is not a law; it's just a prediction. Moore was the Intel co-founder, and Gordon Moore, he proposed that, he saw how the industry is progressing, and he proposed that uh, uh, the number of transistors is going to be doubled in every 24 months. Okay, in the same silicon area. That was a visionary statement. It was predicted around 1965. I will share with you one or two of his papers where he predicted it, okay, in MS Team, so that you can go through that paper and see how what was his thinking and how he made that statement and all that. But he predicted that the number of transistors which will be able to fabricate in the same area of the silicon die is going to double approximately in around 24 months. Okay. Then after this prediction, what happened is like all blue chip companies, all semiconductor companies try to took this as a challenge, and they try to increase the number of transistor and the same silicon die in the same way, or sometime they manage to beat the Moore's prediction. They managed to accommodate more transistors compared to what was predicted by Moore. But anyway, this was like a foundation, or this was like a platform which blue chip semiconductor companies took as a challenge, and started accommodating more and more transistor on the same silicon die. Okay, so this is a very old picture where you see the number of transistors increases. Okay, and this is year. Okay, you see that number of transistor keep on increasing, and these are different it's not clearly visible. So this is Pentium and so on and so forth. How this industry is progressing as the year passing by increasing the number of transistors following Moore's law. Okay. Now, so this was a very important statement, which basically improves electronic industry immensely. Um, let's discuss this in this direction a little bit more, so that we can understand the IC roadmap a little better. So the industries, electronic industry, which we are seeing now, sort of started around 1970s with three main business drive. One was like memory devices. Okay, memory devices. Memory has been very important for any electronic gadgets, starting from computer. So people, one of the fast driving of this, or one of the fast driver is memory devices, as far as the integrated circuit fabrication is concerned. Okay, to the computer industry, memory soon became undisputed volume leaders, because you need to produce many memory devices, right? Because to support your computer, your different electronic gadgets, so you understand the sheer volume of memory devices you need. So this is one driving point as far as the IC industry is concerned. There are other aspects, for example, application specific integrated circuit. So you want to design some circuit which is very application specific. For example, maybe you want to design a circuit for a sensor interfacing. Okay, so that is like a second driving interest for industry, as far as the semiconductor is the IC industry is concerned. That is like ASIC, that is application specific integrated circuit. And the third one is discrete building blocks. Discrete building blocks, these are also very important. For example, different digital logic gates. Okay, op amps, and so on and so forth. So these you can use, these building blocks you can use to make other circuits. Okay, so these are, to be very basic, these are three important driving point to drive IC industries over the years. One is memory, one is application specific integrated circuit, and the last one is building blocks. There's several building blocks out there even today, which you can use to integrate to make complicated ICs. Okay. Um, Now let me discuss very briefly fabrication process step. Again, we will not discuss in detail fabrication steps. If you need to know fabrication steps in detail, you can go through books, or you can go through. There are other courses like VLSI technology course offered in EC department, maybe in the I think in the next semester, VLSI technology, you can attend that course. That is an elective taken by, I mean, presently Professor Bibhu Datta Sahu of EC department is taking this course. So you can attend this course to understand uh, the fabrication uh, process. Okay. Uh, so could you please mute your microphone? Uh, Now, but let me just briefly mention fabrication process steps. Okay, we start with silicon substrate. We clean it. There are different ways to clean the substrate. There will be lab, those who are in the electronics department of doing MTech or doing BTech in the electronics department. You must have those BTech, you must have encountered the lab before, but those in the MTech, you probably will encounter the lab in the next semester, where we will show how to clean the wafer. Okay, so the first step is cleaning the silicon wafer, because the wafer contains lot of dirt. The wafer contains many may contain many organic molecules, organic or some ions, sodium, potassium ions, and so on and so forth. So you need to clean your silicon wafer. Silicon wafer contains sometimes native oxide on top of the silicon, so you need to remove that native oxide, and so on and so forth. So the first step is cleaning. Okay, that is not shown in this slide, but then you grow silicon dioxide on top of silicon. Then you go through conventional photolithography, which is like you spin coat photoresist onto it. Okay, then what you do, you use a mask. Okay, so usually the chromium coated mask. Okay, and the mask will have like some opaque space and some transparent space. Okay, like here, so these are opaque space, and this middle portion is transparent. So when you put mask on top of your wafer and exposed with UV light will pass through this transparent portion and change the property of the photoresist depending on positive or negative photoresist. Some part will be hardened and some part will be softened of the photoresist, and you can remove the resist, okay, using a developer. Okay, and you can then open a window, and you can then remove this oxide layer by etchant. Okay, for example, buffer in the HF acid, in the hydrofluoric acid, and so you can use that to remove SiO2. Okay, and some chemical agent to remove SiO2, and then you have a window like this. You also remove your photoresist, and you have a window like this, and so sorry. So so then what you can do, you can then deposit again oxide layer. Okay, for your gate you deposit polysilicon, then you use you can use a technique like diffusion or ion implantation to realize your source and drain. Okay, then you again deposit oxide layer, you remove oxide layer from here, and you deposit metal to take source and drain contacts, and so on and so forth. So these are basic steps. I have not it is not in very detail, just laid down some of the important steps to fabricate a MOSFET. Okay, there are other processes, the steps in between, which you, if you are interested, you can go through books or net. So this is, you see there are several steps required to fabricate your device, and so all these are automated so that you can have like you don't have to do it manually. All these are automated, and the silicon wafer we can have millions of these devices. Okay, so this so you do the fabrication layer by layer. Okay, so when you are making this source and drain here, you make source and drain in all the MOSFET present in your chip. Okay, in one go, right? When you are depositing oxide, you are depositing oxide in the whole the wafer. So that way it is like automated, it is like reducing cost. You are not making individual MOSFETs. Okay, you are making layer by layer, and the same layer you are depositing all over the wafer depending on where you need. Okay, so that is how this is why it is called batch fabricated, because you are doing things in batches and you are making devices in millions or billions in the wafer, right? Now why it is not. So again, so this is an image of silicon wafer, you see. Okay, the wafer can be from 1 to 2 inch dia to even 12-inch dia. Okay, 12-inch diameter. So you can see that in these several billions of devices you can make on a single silicon wafer, and you need clean room. You need to use you need to cover your hair, your eye, your nose. You have to wear a different kinds of clean room dress. Okay, and you have to wear gloves, because our fingers often contains different sodium potassium ions, which if it goes to your silicon, it might change your device performance, particularly if it goes to the silicon dioxide, I mean the gate oxide layer. Then it will change, it will keep on changing the threshold voltage of the MOSFET. So that is not good. So you need to wear gloves. Okay, you can't handle your chip or your wafer with bare fingers. Okay, and this lithography process usually takes place in a yellow room, so that because white light often interact with photoresist and change its property. So you need to do lithography in a yellow room, and the entire process, fabrication process, is usually done in the clean room. By clean room I mean is there will be less number of particles in that room, because you see that your devices is maybe few tens of nanometer. Okay, which is of the order of dart, which is of the order of size of the particle. So if you have particle around you, if it sits to your device, your mask, so that will change, that will say, for example, if it sits, if it goes here in the mask where there is a transparent portion, if one dust particle goes here, then the UV light will not be able to pass through that portion. Okay, and it will be considered as an opaque area. So whatever device you are making will not work, because some part of the device you fail to fabricate. Okay, because UV light couldn't go through that dust particle, and then the photoresist will be there, it will not be removed, and the device will not make a fabrication will not be perfect. Not only in the masking layer, if the while you are fabricating the device, if the dart will go inside, it will change the property of the device, and your circuit will not work. So it is ideal to use clean room. There are different kinds of clean room people use. For example, class 10,000, class 1,000, class 100, and so on. So by class 10,000 I mean there will be maximum 10,000 particle will be allowed within I think within 1 micrometer cube area. Okay, 1 by 1 by 1 cube area, maximum 10,000 particle. I can't remember, maybe one few micrometer of size. I can't remember exactly. Please look in the net or in the book. If you search as clean room, you will get a lot of information. But so when we talk about class 1000, that means maximum 1000 particles are allowed within 1 meter cube portion cube volume of the clean room. If it is class 100, then only 100, maximum 100 particle is allowed. Okay, depending on the sophistication of your ICs, you might go from 10,000 to 1,000 to 100. Particularly, for example, lithography, sophisticated lithography usually takes place class 100 or below clean room, and so on. So uh, so let me move to let me go to the scaling aspect of MOSFET. What is the scaling? As I mentioned to you already, that Moore's predicted that that we are increasing the number of transistor, or we can double the number of transistor in every 2 years. Okay, what does it mean? It means that you need to reduce the size of the transistor. Okay, you need to reduce the size of your MOSFET. That is what I'm saying, scaling down of MOSFET. Okay, what do I mean by size? I mean by size, I mean WL, TOX, XJ, etc. What is WL? I think all of you know, but uh, let me just those who are not aware, what do I mean by size? Let me just So if I hope all of you know MOSFET. So MOSFET contains source. Okay, say I'm talking about n-channel MOSFET. Okay, source, drain, gate, and so on. So this is my gate oxide. Sorry, my drawing is not very good. You have to bear with me. So this is my gate oxide and maybe gate polysilicon. Okay, so this is your L, that is channel length. Okay, there will be channel between source and drain when you applied a certain voltage at the gate. Okay, so if I so again, as I said, my drawing is not good, but let me try. um, okay, so say this is my source, this is my drain, this is my gate. Okay, so this is L and this is my W. So this is the width of the MOSFET, right? This is TOX, that is thickness of the oxide, okay, TOX, and this is, I am saying, XJ, that is the depth of the junction, right? So when I'm saying I need to reduce the dimension of the MOSFET or size of the MOSFET, so that we can the number of transistors becomes double in every 24 months, right? So this is number of transistors. Number of transistors will be doubled in every 24 months. That means we need to reduce the size of the MOSFET. Okay. So that is also known as scaling down. Okay, scaling down. Sorry, scaling down of MOSFET. So what I have to do? I have to reduce W. I have to reduce, that is MOSFET width, MOSFET length, uh, thickness of the oxide, uh, junction of source and drain, junction depth, and so on. We need to reduce it, right? So right. So how this is good? Why do I need to increase the number of MOSFET? How it is going to help? Because that was the prediction of the Moore. Now, if I increase the number of MOSFET in the same silicon area, clear advantage is um, whatever circuit you are making, it will take less space, right? It will take less space, so you can make your chip more compact, okay, more compact, more lightweight, very tiny you can make it, right? uh, and also if you bring source and drain closer, if you bring not only source and drain close by reducing the distance between them, that is the L, your channel length you are reducing, you are also bringing for fed devices closer to one another, because you are increasing the density of the devices. So this will increase the speed, right? Because then the carrier needs to travel less, right? So so it will increase speed of operation. uh, Number of circuits per unit area will increase. So lower cost, of course, per function, right? So whatever circuits you have before, now you have more circuits on the same silicon area. Silicon is expensive, right? So if you can have like the more circuits on the same silicon area, uh, the cost per chip or cost per circuit or cost per function will reduce. So it has immense benefit if we can reduce the dimension of our active device, which is MOSFET. So that is why Gordon Moore proposed that we should look for reduction of the device size. That means we should look for doubling, at least doubling the number of transistor in every 2 years in the same silicon, so that all these advantages we can get. Okay, so that is why once this prediction was done, a lot of industries jumped into it and tried, as I mentioned, tried this, took this as a challenge. Now here I have tabulated some of the things. If I just go through, one is transistor dimension, as I mentioned, okay, W, L, TOX, XJ, all these dimension needs to be reduced if we want to reduce the size of the FET. Okay, definitely W and L needs to be reduced. TOX, XJ is uh, they also needs to be reduced. They don't have any specific implication in reducing the device size, as you can see, because TOX and XJ, they don't have, because W and L is L say here and W is this direction. So these two, if we can reduce, overall device size or device footprint is going to reduce. But we will see TOX and XJ needs to be reduced as well to keep the device performance intact. Okay, we can't keep TOX and XJ of the same value while reducing L and W, right? Now, this scaling or reduction of MOSFET dimension, we follow different rules for doing that. One of the rule is constant field approach, or one of the method or methodology or approach is constant field approach. Another approach is constant voltage approach, and the third one is generalized approach or generalized scaling. What is constant field approach? Constant field approach is when you reduce your MOSFET size, okay, you also reduce the voltage in such a way, that is the supply voltage. You remember, those you know MOSFET, you need to give the source supply voltage between source and drain, and also need to give supply voltage between gate and source. So these two voltages needs to be reduced in the same proportion so that your field remain the same. Okay, so that is called constant field approach. Your field remain the same. What about constant voltage approach? In this approach, you reduce the voltage in the same proportion. Okay, sorry, I am telling the wrong thing. You don't need to reduce the voltage, because you need to reduce, if you reduce the voltage same proportion, you will get the constant field. If you reduce the dimension but doesn't change the voltage. Okay, so if today's MOSFET I am driving with 1.1 volt, in the next node, by next node I mean when when I reduce W and L 2 years down the line, I will keep the voltage same, supply voltage same. So that is constant voltage approach. Okay, and the third approach is generalized approach or generalized scaling, where we don't follow exactly constant field, we don't follow exactly constant voltage, we go somewhere in between. Okay, so let me go through some of the parameters which I have jotted down here. So let's look at constant field. So say alpha is a parameter which is more than 1. So if it is in a, if today the MOSFET length is L, width is W, 2 years down the line, what I am going to do, I reduce W and A alpha L, TOX and XJ by alpha times. Okay, so the next generation of MOSFET, it will be W by alpha, L by alpha, TOX by alpha, and XJ by alpha, right? So alpha is a parameter which by which we are going to reduce the dimension. Okay, so if I do that, we have to reduce voltage also in the same proportion so that the electric field remains the same, right? Now we can see capacitance. Okay, capacitance is epsilon A by TOX, right? That is capacitance. What is A? A is W multiplied by L is A, that is the area. This is gate capacitance. Okay, epsilon A over TOX. And if you reduce A and reduce TOX, so we will, I think we will discuss this in more detail from I think from Rajavi's book. From Rajavi's, let me just yeah, so the book is Rajavi's book on design of analog CMOS and integrated circuit. Okay, I don't know. Let me. I'm not sure it will be visible or not. So, design of analog CMOS and integrated circuit by Rajavi. This book at the end has a few pages on scaling down. Okay, I will cover that part, and I will see if I have a if I have a um, scanned version of those few pages, I will upload in the MS Team. That is basically on how this MOSFET and where is the presentation? Yeah. So yeah, in the book they have shown how these parameters like gate oxide, gate capacitance, current, delay, and so on and so forth. They have done some small mathematical calculation. I mean, they are very easy, but we will do it in the class just to see like whatever I have written here, those are correct or not. Okay, and then you will get a little bit more insight. Okay, but for the time being you just believe what I am saying now. Okay, please believe that. So gate capacitance will be reduced, current will be reduced, current in the MOSFET maybe in the saturation region will be reduced, delay, power dissipation will be reduced. Okay, but power density will remain the same, right? So this is constant field approach. What is constant voltage approach? Again, in the constant voltage approach also you are reducing the dimension you have to reduce all the time, because that's the fundamental requirement. Okay, what about voltage you are not reducing, you keeping the voltage same. Okay, now if you keep the voltage same, your electric field is going to increase by alpha times. Okay, because this is V over D, you are decreasing D but keeping the voltage same. Okay, that way you are increasing the electric field, and so on and so forth. Here power density is going to increase. Okay, whereas here dissipation going to increase, here power dissipation going to decrease, but here you see power dissipation going to increase and power density increases enormously if you follow constant voltage approach. Now in constant field and constant voltage approach has their own merits and demerits. Some of them probably you can already guess. In constant, if you follow strictly constant field approach, you are reducing the supply voltage. Now if you are an analog design engineer, okay, and you are designing your circuit, you might need to put several, for your specific, for a circuit you might need to put several MOSFET between rail to rail. For example, don't know, for example, what I can yeah, for example, say you are designing an op amp. Okay, you're designing an op amp, you all know that in case of op amp maybe you need you uh, you have a biasing transistor, and you have like two uh, and then this is a current source, and so on and so forth and so on. Okay, so say you see this is VDD and ground, right, and so on. So this is just an example coming to my on top of my head now. So you see there are three transistors between rail to rail, you see. So you have to make sure all these transistors is in the saturation region. Now if you keep on reducing your VDD in every next node, in every 2 years down the line, if you keep on reducing this VDD, it will be very difficult for the analog design engineer to design the circuit, you see. Okay, so constant field is very good because it is reducing um, the you see the power dissipation. Okay, it is reducing the delay. It's very good constant field approach. But the thing is you it is very difficult because you are reducing voltage, supply voltage, for very difficult for the analog design engineer to design circuit. So analog design engineer are not happy with constant field approach. They said like we can't design the circuit if you keep on reducing the voltage. Okay, supply voltage. What about constant voltage approach? Constant voltage approach has its own demerits. What is that? You are keeping the voltage constant. If you keep on keeping the voltage same while reducing the dimension of the MOSFET, your electric field will increase at the same proportion. And if your electric field will increase, the device will be, reliability of the device will be an issue, because electric field might be very high between source and drain, electric field might be very high between gate and your substrate, okay, because you are keeping the voltage, supply voltage same. So then this approach will help the analog design engineer. They say, oh, that's very good, because voltage is not reducing, so we can design our circuit very well, okay, with proper headroom and all that. But the thing is, here you see the field, the high electric field might make your device unreliable, okay, there might be a lot of leakage current and so on and so forth, device might breakdown might take place, okay, although but delay wise you see constant voltage approach is very good delay wise, okay, reduce delay enormously, although power density will increase, so it will heat up the chip more and more, okay, compared to constant field approach. So so as I said, constant field and constant voltage has their own merits and demerits as far as the scaling down of the MOSFET is concerned. So people started or industry started moving to some generalized approach. So then they don't reduce they reduce the dimension by alpha, but they don't reduce other parameters by the same proportion. For example, they will use k by alpha instead of alpha as far as the voltage reduction is concerned, okay, they will reduce the voltage but not as aggressively as the dimension of the MOSFET, okay, so that makes analog design engineers happy, okay, and that also not increase the electric field that much, okay, and so on and so forth. So these are different scaling down approaches. As I mentioned that I will go through some of these parameters, and particularly in the constant field approach I will go through some of these parameters and calculate in front of you to show that how these parameters are changing with reduction of the device size, okay. um, Probably tomorrow or maybe next week, okay, but let's carry on and discuss what we are discussing now, so that we can maintain a flow and you understand what I am talking about, because this is a little bit different branch we will take on, which we will take on later, right? Now if I keep on talking about this scaling thing, which is very important and which ultimately lead to this nanoelectronics research, okay, you see the transistor count kept on increasing with new node. What is new node? Um okay, new node. Do you know what is node? Any of you know what is node? Do you know what is node? Any of you? So am I muted everyone, or you can unmute yourself and talk? So nobody is speaking. So any of you know what is node?
Sir, is it related to the physical, the size of the transistor?
Right. So this is related. This is correct. So this is related to the size of the transistor. So those who have done some design using cadence or synopsis or metrographics for their circuits, okay, they probably come across this term node, or process node, okay. um, what we do, we ask fabrication lab, like I want to fabricate my device, my circuits using quote unquote a particular process node, okay. Now this particular process node is probably you have heard say 180 nanometer process or 330 nanometer process. So these are specific process node or 1 micrometer process. What I mean is that the length of the minimum length of the MOSFET support by that process is 1 micrometer. or if it is a 330 nanometer process, minimum gate length, that is the channel length L, is 330 nanometer in that process. Okay, so if I go to a, so say if today's process node is 22 nanometer, okay, next that means that minimum gate length is 22 nanometer. Next process node or new generation process node might be 14 nanometer. That means the minimum gate length which is possible to fabricate by that fabrication lab using that process node is 14 nanometer. Okay, so that's the minimum gate length. You can use much higher gate length if you want. Actually, analog design engineer often use that. Okay, whatever it is the gate length, they use larger gate length compared to what is minimum gate length available, because they want to reduce the effect of channel length modulation in MOSFET. Probably you have heard channel length modulation, but digital design engineer often use minimum gate length which is available from a process. Okay, so anyway, so this node, by node I mean by node I mean a process which is available by the fabrication lab or which is supported by the fabrication lab, having a particular minimum dimension of MOSFET. So that is basically process node. Okay, by process node it means like what is the minimum gate length possible, right? So as we move to every 2 years, say, electronic industry is coming up with a new process node, because as we are discussing, we are reducing the size of the MOSFET. Okay, so we need to, so that we can accommodate double number of MOSFET in the same silicon area. So so every 2 years, roughly every 18 to 24 months, we are having a new process node. Okay, we will have all the old process nodes, most of the old process nodes as well. That depends on the fabrication lab, and that depends on your requirement also. If you want to make very high speed ICs, you probably need to move to lower process nodes. Okay, but if you don't need that, you might use maybe 1 micrometer process or 330 nanometer process. Okay, but if you need very high speed state of the art processes, you have to move probably 45 nanometer, 22 nanometer, 14 nanometer. Maybe now we are in the 7 nanometer regime, around 7 nanometer or so. Anyway, so if you, so the transistor count kept on increasing with new node, which is obvious, which we have already discussed, because we will have more transistor on the same silicon area. But frequency increment was sacrificed. Okay, frequency increment was sacrificed. What do I mean by frequency increment? Frequency increment means clock frequency. Okay, so if you we all want, actually we all want like high speed electronic gadgets. So whenever I buy a new laptop, or when I buy a new mobile phone, we always look for what is the clock speed, what is the speed of the processor, how fast it is, and so on and so forth, right? But if you I don't know you have looked it carefully or not. If you look carefully, this speed hasn't increased much over the last few years, not increased significantly. I'm not talking about charging speed, charging of gadgets. I'm not talking about that. I'm talking about speed, clock speed of your electronic gadgets or your laptop or your mobile phone. That didn't increase much over last few years. But if you look like 10, 15 years, 20 years down the line, it increased a lot. But in last few years, probably it hasn't increased much. So so that is what I wrote here. The frequency of increment was sacrificed from mid of last decades. Okay, to keep the temperature dissipation within thermal budget. You see, here I showed like power density remains constant with constant field, but as you use constant voltage approach, power density increases. As you increase generalized, as you take approach of generalized scaling, there also power density will increase. Okay, in other words, as you cramp more and more devices, it will be it will be more, the chip will be heated up, okay, more and more heat will be generated, okay. So what people tried to do, people accommodated more devices but didn't increase the clock frequency in the same rate, okay. So that is what I try to mention here, so that they manage to keep, so that they keep the temperature dissipation within certain thermal budget. So that is one aspect. Another aspect is this limitation of maximal usable frequency have impacted computer industry. Why? Because in the computer industry you want your processes should go very fast. Your processor should perform all the operation in much faster fashion what it used to do in 5 years before, right? So there is a conflict between the requirement. One part of the industry wants more faster clock frequency, okay. So but it is not easy to achieve that, as I said, like there will be dissipation of lot of power that will increase temperature heavily. People adopted other approaches. For example, you do things using clever architecture, clever algorithms, okay. For example, single core to multi-core and so on and so forth. So that sacrifice in the frequency have been addressed through different means, okay, not like through increasing the frequency of the clock in the same manner, but by using like clever software algorithm or clever architecture and so on and so forth, okay, intelligent architecture and so on and so forth. Now I'm tempted to discuss this, although I haven't, as I said, like I will discuss this part a little bit more detail from the Rajavi's book, but I'm tempted to discuss this part which will be there in the Rajavi's book as well, not in this fashion but in some other fashion. So if we keep on reducing this MOSFET size, there will be a lot of issues, okay, lot of problems. Those problems are known as short channel effect. Those problems are known as short channel effect. What is known as, maybe again you have heard this term, short channel effect. Let me repeat it once more. What I'm saying, so I'm saying that we are reducing the dimension of the MOSFET size. If we keep on reducing the MOSFET size dimension, there will be a lot of challenges, very difficult. Initial days it was probably easy, but as the things are progressing and we are like really trying to reduce the MOSFET size, in every 2 years we had some deliverable that we need to reduce this much, this much, this much, and we end up with a lot of challenges, okay. So those challenges are known as short channel effect, okay. Those effects are still there, some of the effects are still there, but every now and then we have new discoveries, new inventions, okay, to overcome those potential barriers, to overcome those barriers, right? Not potential barriers, those to overcome those barriers. Now one of the short channel effect I am tempted to talk now, we will talk short channel effect in more detail later on when we will go through Rajavi's book, is, you see, we are reducing the dimension W and L. We also need to reduce the dimension of the gate oxide. So this is my, say, my gate oxide, okay, Tox, the thickness of the gate oxide. Now why do we need to reduce the dimension of the thickness of the gate oxide? Now if we don't reduce the thickness of the gate oxide, what will happen? We will not have enough control from the gate side, okay. But let me just So I have a long channel MOSFET. Okay, again I am drawing NMOS. Let me use it with, yeah, okay, no. So gate oxide, this is polysilicon, right? This is my long channel. Okay, this is L. Now what we are doing, in we have reduced the dimension of the MOSFET. Okay, L1. So L1 is much less than L. Okay, so now what I am saying, that I also need to reduce the thickness of the oxide. If I don't do that, what will happen? If I don't do that, the electric field between source and drain will be larger. So we need to increase the electric field from the gate side also, so that we can control the channel. Okay, because in MOSFET you see, you form the channel by applying voltage at the gate. Okay, so here whatever be the thickness Tox, here Tox needs to be reduced, right? Here Tox needs to be reduced. Why Tox needs to be reduced? Because if we can't reduce the Tox, we will not be able to control the channel. We will not be able to control the channel from the gate side. Now, if you keep on reducing your Tox, it might happen one day that the oxide layer will be just few atomic layers. Oxide thickness is so low, it might be few atomic layers of SiO2. Okay, so that can create problem, because the current, the electrons might be able to pass through this gate oxide and create lot of leakage current, and that may be create reliability issue of the device, because the thickness of the gate oxide will be very tiny, maybe just few atomic layers, not easy to fabricate also. Even if you fabricate, that might create some reliability issue, right? So this is one of the major, this was one of the major challenge. So what people did, uh, people use people use high K dielectric to address that issue. Okay, what is high K dielectric? So instead of silicon dioxide as a gate oxide layer, they started using other insulating layer which is of higher K value. How that will help? If you look at this formula, all we know, C is equal to epsilon A by Tox, right? Capacitance, gate capacitance. Now, this capacitance of the gate oxide, okay, capacitance of the gate oxide will improve if you reduce. I'm not talking about A for the time being. A for the time being, I'm not talking about. Okay, so if we reduce Tox, then only this capacitance will improve, right? You remember we mentioned that this Tox we have to reduce also. So that is the reason. This is the reason why we need to reduce Tox. So if we reduce Tox, then we will have better control from the gate side. Okay, we will have better control from the gate side, because if you reduce TOX, you will be able to increase the capacitance. Okay. Now if we reduce TOX, it will increase the capacitance, but it might increase the leakage current through the gate oxide. It might make it might create some reliability issue at the gate. So what we can do, instead of using reducing TOX, we can use a different material with higher K value instead of SiO2. So what is the K value of SiO2? Dielectric constant of SiO2? Dielectric constant of SiO2 is around 3.8. Okay, so this dielectric constant of SiO2 is around 3.8. So if we use some other material which is like an insulator having higher K value, then we don't have to reduce TOX that aggressively. Even if we don't, even like W and L, we are reducing W, we are reducing L, we don't have to reduce TOX that aggressively, okay, to achieve control from the gate side. If we replace silicon dioxide with a high K material, okay, or high K dielectric. So that is what I have written here, like leakage current due to tunneling between gate and channel increased, and this will increase power loss if we have like very tiny thin gate oxide, and reduce device reliability. This is what I have said already. Now replacing SiO2 with oxide having higher K value, this will do what? Higher capacitance with large oxide thickness, hence much lower leakage current and more cooler chip, right? People started using, in fact nowadays present days MOSFET, they don't use silicon dioxide as a gate layer, they use HF hafnium dioxide or zirconium dioxide as gate layer. Okay, you see they have like much higher K value compared to that of SiO2. Okay, this is some old data in 2007 2008. IBM published that by changing SiO2 some with a different high K material, uh, okay, leakage may be reduced by 5 orders magnitude. Leakage current is very important, you see, because your chip might contain few millions of transistors. So if you manage to reduce leakage current, okay, that have enormous impact, enormous benefit, right? And this reduction in leakage current and increase in TOX, because you don't need to reduce TOX that aggressively if you use high K oxide layer. So in that case you will be able to continue your scaling of MOSFET, right? But if you can't use high K material, then your with the SiO2 we were like very only few atomic layers, which is very difficult to fabricate also, and also very difficult to have a like reliable uh, gate oxide or reliable MOSFET, right? Okay, so now we are going to discuss something else. Else doesn't mean like we are still in the IC roadmap and what is the implication of scaling down, but we are discussing metal gate and polygate now. So do you know why any of you know, like what was the gate material in MOSFET, like around 1970s or 1980s? Do you know, any of you? So on top of oxide, sorry?
Aluminum.
Yeah. So on top of oxide, it was aluminium, right? That is how this metal oxide field effect transistor, metal oxide semiconductor field effect transistor. So this, it was initial days, it was uh, this was metal, okay, and it was made with aluminium oxide semiconductor. So that is how metal oxide semiconductor, then FET, field effect transistor. Just don't worry about it for the time being. So this was metal, okay, and it was made of aluminium initial days, right? Then people moved to polysilicon. Can anyone tell me why? Do you know why then we moved to polysilicon? Surendra, you know why?
Sir, it is also from fabrication point of view. I know that that will lead to self alignment of source and drains.
Right, right. Any other answer? That's correct actually. Any other?
Now I can't remember,
Okay.
sir.
Sir,
Okay. Yeah.
sir, if we deposit the metal and if we try to do the diffusion process, since the diffusion process is a very high temperature phenomena, so due to the this high temperature, the aluminum cannot actually tolerate such a high temperature. That is why
Right.
we go for
Right.
the polysilicon.
Right. Right.
And sir,
Perfect.
I'm not sure. I think it also creates a problem in the Birdsbeak formation. I mean, the expansion coefficient are not the same for the aluminum and the substrate. So
Right. Right. Okay. Okay. Right. Let's not go into the Barsvik direction, but you are right. Both Shubhendra and you are right. Actually, we started with aluminium as gate material on top of gate oxide. Then people moved to polysilicon. So what I mean is, instead of instead of metal we have polysilicon here, okay, instead of metal we have polysilicon here. The reason being, aluminium melting point, as your friend suggested, said, is only 660 degrees centigrade. Okay, aluminium melting point is only 660 degrees centigrade. Now if you use aluminium, it has to be at the very last. You can't make aluminium get fast and then do other processes. Okay, if you remember, no, not this one. If you remember my where is the presentation? Yeah, if you remember this, here you see we have created oxide, then polysilicon, then create source and drain. Okay, this is either diffusion or ion implantation process. Okay, diffusion process usually very high temperature process, as your friend suggested. Ion implantation is not very high temperature, but still, you after you create this source and drain, you need to anneal it. What is annealing? Annealing is a high temperature treatment, so that whatever defects is generated for this source and drain creation, you need use high temperature so that those defects goes down. Okay, because by doping you are basically incorporating foreign materials like phosphorus or boron inside silicon, right? So there is bound to be lot of defects, and those defects needs to be reduced by high temperature process. Now if you use aluminium, you can't realize this gate fast. You have to create your source and drain, then you have to realize your gate, because aluminium can't sustain high temperature, right? I mean, that is not a big deal. You can make your gate later, okay? That should not be a problem. But the thing is, so there are other problems. One of the problem which Surendra pointed out is self alignment. What is self alignment? Now, what we usually do, we make gate, and then gate acts as a masking layer for source and drain. Okay, how to make you understand this? I'm not sure. Okay, so our vision is, I mean, gate has to overlap with source and drain. If this here it is overlapped, here it is overlapped. If it is not overlapped, the channel will not be continuous, right? If if the gate, if the gate finishes here, say for some reason, okay, then what will happen? Oops. Here the channel will be broken, right? So gate overlap with source and drain is a must, right? Now if you follow gate last approach, which is aluminium metal gate, okay, because as your friend suggested, aluminium can't sustain high temperature, so you can't have like diffusion and annealing, all that after having gate. So if you have a aluminium gate, your fabrication of gate has to be later, after realizing source and drain, right? Now if you do that, scaling down will be an issue. Why? Let's just put some numbers. Say I have 1 micrometer process. So minimum gate length is 1 micrometer. Not only that, my lithography process resolution is 1 micrometer. Okay, that is why I can realize 1 micrometer gate length, right? So minimum gate length is 1 micrometer or 1 micrometer process. That is the resolution of my lithography system, which I mean through the lithography system, the resolution I can achieve is around 1 micrometer. If that is the case, and if I say this is my 1 micrometer, okay, gate length. Now I have created source and drain, and now I am forming gate. So if I form gate, I need 1 micrometer this side, and my drawing is not up to the scale. So here I need 1 micrometer also, here I need 1 micrometer also, because I can't realize any dimension below 1 micrometer in this 1 micrometer process, right? So you see, the footprint of my device is going to increase, and it is difficult to scaling it down. What about gate fast approach? What is gate fast? So I am realizing gate fast, then I am having my source and drain, which I have shown you in the that basic process steps. Okay. Now in the gate fast approach, you realize the gate. We realize the gate. So this is my gate oxide and my gate material. Which is, what is that gate material? Will be people did it with polysilicon. Ah. Then I am realizing my source and drain. I am doing diffusion or ion implantation. So what this diffusion or ion implantation will do, this will diffuse my phosphorus or boron ion here, okay, but this is not, this will also, this phosphorus and boron will move not only vertical direction, in little bit in horizontal direction also, okay, and that is good enough to get the overlap. Little bit tiny overlap will be there, right? So that is known as self-aligned gate or self-alignment. Self-aligned gate or self-alignment, as your friend Surendra suggested. Okay, if you have like gate fast approach, where you have like gate oxide, and in that case you can't realize aluminium, you can't use aluminium, you have to use polysilicon. But if you use polysilicon and then you realize source, because polysilicon can sustain very high temperature, so then you do source and drain diffusion or ion implantation, you do annealing, that is not a problem. But what this will do, you see now, even if this is a one, say this is my 1 micrometer process, but this part I am not achieving through lithography. This is automatically happening because here gate is acting as a masking layer, and while diffusing or ion implanting those phosphorus or boron ion, they not only move vertically, some of them little bit will move little bit horizontally also, okay, right, and give us this tiny overlap which is good enough to achieve that overlap actually, right? So as you see, for reducing the device dimension, gate last approach is not good. So people move to polysilicon. So basically the temperature is an issue. Polysilicon can sustain high temperature, and using polysilicon we can have self-aligned gate, that is gate last, which will help us in reducing the overall dimension of the device. In both the cases, here and here, gate length is same, but gate length is not the whole thing. Ultimately you have to reduce the size of the device, okay, but if you have like this overlap is so much, that will also create capacitance here, and also it will be difficult to reduce the overall dimension of the device, right, because we have to have this overlap, and this overlap will be limited by the resolution of your lithography process, which is not the case if you use gate last approach. And gate last approach is only possible if you remove aluminium and use polysilicon, right? I hope this is clear to you. I tried to do it very slowly. We will keep on discussing this in the next class. So metal gate versus poly gate. So just to give you one more info, nowadays most of the polysilicon, I mean this low CMOS node, the gate is no longer made with polysilicon again, okay. So we are moving, or we have moved from polysilicon to metal again, but that's not aluminium, that's some other metals, because aluminium can't sustain, as you already know, high temperature. So the metal is, now the metal is different. We are not using polysilicon again, the reason I will tell you in the next class, and from here we will start again in the next class. But please tell me if you have any doubt, if you have any question, you please raise your hand, or you can ask me directly, because it's only 33, 34 students, so we can take direct questions. Otherwise, we will stop the session.
Sir,
Yeah.
sir, when we say that we want a good gate control, does it same as saying we want high capacitance?
Good question. No, it's probably high capacitance is a loose term probably. But the thing is, in scaling down, your capacitance is going to reduce, as you said, because there is a epsilon A by Tox, right? A
Yes,
is,
sir.
if you reduce, you have to reduce A, that is W and L, so it is, there is alpha square. Probably you are pointing out that. So that's basically, so C is equal to epsilon A by Tox, right? So in the C scaled, I will say next node, it will be epsilon A by alpha square and Tox by alpha. So overall this C scaled will be lower than C. So C scaled will be C over alpha, right? Because this is alpha square, this is alpha. But the thing is, the way we look at it, that we need better control from the gate side, and better control can be achieved if we have like reduction of Tox. And if you reduce Tox, effectively your if we don't, if you are not talking about scaling now of A, okay, scaling of A will be always be there. Now if we reduce Tox, then only your control from gate side will increase or improve, and by reduction of Tox means capacitance will increase, right? So what you have to do, like you have to, we initially reduced Tox, but at some point we couldn't do, and then we started changing our dielectric. Is that what your, is that answers your question?
Yes, sir. Yes, sir.
Okay. Um, Anyone else?
Sir,
Yeah.
when we use polysilicon, then it also reduces the overlap capacitance. Then my switching transistor switching speed will increase or it will be same.
So if I use polysilicon, that overlap capacitance will decrease, right?
Yes, sir.
Yeah. So your question is whether it will improve, whether it will improve speed wise.
Yes,
Is that
sir.
what you are asking?
Yes, sir.
It should improve speed wise. Okay. Um, but I don't have on top of my head the formulas maybe associated with it exactly, but it should reduce the delay associated with it, because any capacitance you have to charge or discharge, right? So the higher the capacitor, uh, it will ultimately create problem. If I think you should look for in the net or in the book, otherwise I will tell you in the later class um, what effect it will have, but it will definitely, um, if we manage to reduce the overlap, it will have positive effect.
Okay, sir.
Anyone else? Okay, so if not, then I think we almost 10 now. You might have other class from 10. So stopping here now. So what I will do, we will meet again tomorrow. Tomorrow what time? 12 o'clock, right? 12 o'clock or 11 o'clock? 12 o'clock, right? Yeah, 12. So we'll meet at 12. Okay.